Good afternoon to all. Welcome to this 30th session on experimental methods in thermal engineering. Till this lecture, we have discussed about the measurement of individual parameters. Like, for example, if we have to measure a pressure, then what are the different instruments available for measurement of the pressure? Then what is their limiting range? What is their accuracy? What are the principles based on which these are actually giving us the value of pressure. Then similarly, we have seen for the measurement of the flow, measurement of the temperature, heat flux. Then we also saw the measurement of individual properties of different fluid mediums. Okay, so different techniques which are available. So as a individual entity, we have seen now different things. Now here comes one important task that we have to actually acquire the output signal from all these different measurement devices. And another important task comes that if we have to design some experimental device, then actually we will not be having measurement of a single parameter. Rather, we have to go for measurement of multiple parameters, and then based on that we will be deriving some output. Okay, so now we will be seeing that we'll take a physical situation, and in that physical situation we will be having certain requirement from the experimental setup, and then we will try to see that what type of measurements, what mountings of the different instruments we have to do. Okay, so now what we have to do, basically whatever we have studied in this subject uh, till this lecture, we will now try to combine all that information in order to design a detailed experimental setup for obtaining some output particularly related to the experiments in the field of fluids and thermal engineering. Okay, so we have also seen that we are having the different instruments available. Majority of the two routes based on which we obtain the output signal from an instrument is either by mechanical arrangement or with the help of some electrical arrangement. In case of mechanical arrangement, we are having some mechanical levers, etc. are there, with the help of which we try to obtain some readout based output. And in case of electrical instruments, what we are having, our output signal is either in the form of resistance, current, or voltage, okay, depending upon the principle of measurement. And then we try to uh, calibrate that output signal to that of our physical quantity. Okay, and particularly the advantage with electrical instruments is that we can acquire this electrical data. Okay, we can store that data, and then we can further post process that data in order to obtain some desired output. And at the same point of time, if we have to control some parameter, then obviously uh, by using that output we can utilize it for controlling other different process parameters. Okay, so in this particular lecture, what we will do, we will first see about the general layout of data acquisition system, and then we will talk about design of experiments. Okay, so particularly for data acquisition system, I will not give you very much details, because already you know that nowadays we are having large number of systems available for acquisition of specific type of data. For example, if I have to measure temperature, then I will be having some another module for current. I'll be having another module for pressure. We are having some specific modules available. At the same point of time, we are having some generalized modules also available, over which actually we can mount these individual specific property specific modules. Okay, and even different softwares also are provided by various commercial manufacturers of these data acquisition systems. So uh, depending upon our requirement or the cost of the different devices available in the market, one can select commercially available devices. Okay, and moreover, whatever the data acquisition system devices are available in the market, actually these are subject to rapid transition. Rapid transition means, for example, whatever the system we were having available 5 years before, now that system is obsolete, and we are the commercial vendors are actually coming up with some new data acquisition systems which are more giving the faster rapid acquisition of data. At the same point of time, we are actually having low size. So earlier data acquisition systems, if you try to see, they were used to be very bulky. Nowadays we are having very compact units, and at the same point of time we are having many softwares available with the help of which we can actually do further post processing of our data. Okay, so that's why in this particular lecture I'll be only talking about the general layout of data acquisition system. Then second part of the lecture is design of experiments. So what I'll be doing over here, first I'll give you the generalized classification of various type of experiments, okay, depending upon our requirement. And once we have got the appropriate classification for our experiment, then we are having certain experimental protocols and procedure that what are the different things that we should actually different activities that we should plan in order to design our experimental setup. Okay, so initially, first I'll give you the brief categorization and classification of different protocols, and then with the help of a case study, we will try to see that how to implement all these different procedures in order to design experimental setup for a given physical situation. Okay. So in case of data acquisition system, what I am showing over here, I am showing a general data acquisition system. So nothing but in a data acquisition system, what we want to do, we want to measure a physical property. So obviously that physical property, whichever we want to measure, that will be acting as an input to the transducer. And from the transducer, we will be getting certain output. Obviously, in order to post process, in order to obtain that output in the desirable form, we will be having some input circuitry as well as some signal conditioning system. Okay, so it may happen that from some system we are getting say current output or voltage output which is of very small magnitude, and at the same point of time it can also contain some surrounding noises into our signal. Okay, so what we have to do, we require certain circuitry for removing that noise from the signal. At the same point of time, we need to sometimes amplify our signal depending upon the requirement. Okay, so another then what we will be doing once we have obtained the conditioned signal from the transducer, then obviously we will be having some transmission system which will be transferring that to the processing unit. Okay, and what this processing unit will be doing, this will be actually converting our signal from one form to another form, and finally we will be having some output unit where we will be actually getting the display of our quantity or physical parameter which we want to measure, and at the same point of time we may have some storage of the data if we want to use it further. Okay, and at the same point of time, once we have obtained the value of a physical parameter, then depending upon its present value we may need to do some action in order to control that parameter. Okay, so it may pass then to further systems for processing. Okay, so this is the overall layout. So you can see over here we are having some input module. Inside the input module we are having transducer and signal conditioning circuitry. Then we are having transmission and processing units. So generally transmission and processing units involve small microprocessors or microcontrollers, where actually we will be having input in the form of either because particularly we are now talking about current electrical output based transducer. So we may have output signal in the form of either resistance, voltage, or current. So now then inside the processing unit we will be actually applying our conversion factors from the uh, output signal, whatever we are getting in the form of current, voltage, or resistance, into our physical parameter. Okay, so for example, if we are having a pressure transducer, then obviously depending upon the value of the pressure, if we are getting some output current, so obviously corresponding to say P1 pressure, I am having output current as I1, then corresponding to P2 pressure, output current as I2. So now what we will be doing, when we will be doing the calibration of our transducer, then we will be having the relationship in between the current and the pressure. And as I have already told you that majority of the time when we design our transducer, we try to keep the condition of linearity, that we should have linear dependence between our physical parameter and whatever the output from the transducer we are getting. Okay, so at the stage of calibration, actually we try to relate the variation of this physical parameter as function of the output signal, and whatever the correlation we are getting at the stage of calibration, that we employ in this processing unit for obtaining our physical quantity depending upon the signal whatever we are getting from the transducer. Okay, and then in terms of display unit, we may have actually some computer screen, some digital display. Okay, where we will be actually having access to our data. Now, a typical example of this type of acquisition system you might have seen while you go to your fluid and thermal laboratory. So you might have seen that there are many display units available for temperature. So you are having some RTD sensor or a thermocouple, and then that thermocouple you have connected to that unit, and that unit basically converts the output EMF obtained from the RTD or the thermocouple and into the value of temperature. And sometimes we are using that temperature to control other parameters also. For example, one of the simplest example which I have already given to you earlier also, that if we have to control the temperature of fluid which is actually heated with the help of a heater. Okay, so we are having some PID controller based processing and control units where we are obtaining the value of temperature of our fluid, and then depending upon the set value in our controller, if the process value is actually less than that of the set value, then obviously our heater will be switching on, and if our process value is going beyond or increasing above the set value, then our heater will be actually switching off. Okay, so this is like the general layout of data acquisition system. So in this particular thing, you can see that I have shown only the acquisition of a single physical parameter. Okay, so now say we are having a physical situation where a number of transducers, a number of thermocouples are required. So obviously we will be having number of transducers. So in that case, what we have to do, if we have to acquire the data, then obviously what we have to do, whatever this general layout I have shown, this type of systems, I have to replicate the number of system equivalent to that of the number of physical parameters which we want to measure. Okay, so that will be like becoming a costly, and at the same point of time it will be not feasible to replicate a single unit depending upon the number of channels, whatever number of parameters for which we want to do the measurement. So that's why what we are having certain systems where which provides the access to multi-channel data acquisition. Okay, so in case of multi-channel data acquisition, what we will be having actually number of transducers, and we will be having number of conditioning circuits. But whatever the output from the transducers we will be getting, that we will be passing through a single scanner unit. Okay, so in this scanner unit, we will be nothing but we will be having actually rapid transmission of data. Okay, so what this scanner unit we will be doing, it will be sequentially reading the data. So for example, if I require the acquisition of data at the frequency of 10 hertz, and if I have to measure the data particularly say for 10 different measurements. Okay, so what I'll be doing, my this scanner unit will be actually operating at the frequency of 100 hertz. So what it will be doing, it will be first taking the data from first transducer, that it will be reporting as output, then it will be taking data from another transducer, and that it will be reporting to our post processing circuit. And in that sense, what we can do, if we are operating our scanner unit at high frequency in comparison to that of the requirement of frequency at which we are acquiring the signal from individual transducers, then with the help of a single scanner unit actually we can obtain data. Okay, so this type of data acquisition systems are particularly known as multi-channel data acquisition system. Okay, so you can see in this multi-channel data acquisition system, we are after that we are having some intermediate post-processing circuitry. So here we are having number of circuits available. For example, if we want to convert signal from voltage to frequency, then we are having analog to digital conversion, digital to analog conversion. So different type of intermediate systems we will be having. Then we will be getting some output, and after output we may have different type of display units for obtaining our final physical parameter. Okay, and depending upon the type of the physical parameter which we want to measure, we can choose the display unit. Okay, and at the same point of time, we can employ some computer also in order to store output data and then transmit it for further applications. Okay. Generally, whenever the commercial manufacturers provide data acquisition system, they are providing some their indigenous softwares also, which are actually consistent with their data acquisition system, compatible with their data acquisition system, and with the help of which actually we can particularly do the post processing as well as the acquisition of data. Okay. Now, one of the more generalized system nowadays are also available, where we will be having a single module. Okay, and in this single module then we can actually employ specific property based number of modules. Okay, so for example, if we are having a single system, this particular single system will be a generalized system which will be connecting our transducer to our computer or a software where actually we are acquiring the data, and then over this generalized system we will be having individual modules depending upon the output type of our transducer. For example, if I want to measure a pressure and the output of the pressure transducer is current, then obviously I'll be employing some current module, and that will be actually connecting my different pressure transducers, and depending upon the value of current, then after post processing we will be getting the corresponding value of the pressure. Then on the same generalized system we may employ another module for temperature, where we will be having actually module which will be acquiring the voltage output. Okay, and then it will be having some conditioning circuit which will be converting the voltage signal into corresponding temperature value. Okay, similarly we may have systems for measurement of the flow rate, then and other properties as well. Okay, the only thing common we will be having, that we will be having actually primary measurements of current, resistance, and voltage, and then depending upon the type of the transducer, we will be having specific conditioning, signal conditioning and processing units, where we will be converting our output signal into the specific physical parameter. Okay, so once you are back to the campus, then we can go to the laboratory and we can see some of the data acquisition systems which are available in our lab, and then we can practice different acquisition of different physical quantities, okay, in our existing systems. Okay, now let us try to go towards our second part of this lecture. So second part of this lecture is on design of experiments. So in this particular section, what I will do, I will take up a case study, but before that, let me first give a broad categorization of different type of experiments. Okay, so what I have done, I have shown one table over here, and in this particular table, if you see your row A, so row A is nothing but type of experiment, and for corresponding to this, we are having actually 9 different categories. Okay, so you can see the first type of experiment is actually fundamental research, and this particular fundamental research is based on some government classified norms. Okay, another could be fundamental research, and that is a particularly for open result. Okay, that is of general interest. Then another category is developmental research. So that particular developmental research may be company specific, and next category is developmental research that may be actually once again open to the general public. Then another, maybe we have to do the testing of certain devices based on the codes or standards available. In the next category, we are having testing according to some accepted methods. Okay, then we may have to do the testing particularly for commercial purposes. Then one of the categories, just we want to know that, okay, what will be the effect of some parameter on our output in a particular system. Okay, and then another can be that we have to design some preliminary measurements prior to the experiments which are to be followed in any of the category which are specified over here. Okay, So these are the different categories, and then corresponding to each category, we are having some specific characteristics which are given over here, and then their corresponding requirement for different type of experiments is specified. Okay, so this is a like very theoretical aspect, and I will not discuss this in detail. What you can do, you can simply go through this particular slide and try to see that what are the different characteristics of different kinds of experiments. Okay, then we are having some experimental design factors. So obviously when we are designing the experiment, then first we should be clear about overall objective of the uh, experiment. Then for overall objective, we are having different requirement of the actions, and what will be their results, and what will be the influencing factors. Okay, then we should also know about list of specific results, what we are planning to obtain from our experiments. Okay, we should know about the different samples or formats of results, whatever are required, then what will be the different techniques which will be required for obtaining our final output from the experimental setup. Okay, so based on this, like we are having number of activities which are mentioned over here. Okay, so once again, you can go through this table and you can find out the sequence of these different activities which are to be followed. This is once again a very theoretical topic, so you can go through this particular table. Now, let us try to take one example. So this is a case study, and with the help of this case study, let us try to see that how we are approaching towards designing the experimental setup. Okay, so this particular case study is on forced convection measurement for a new refrigerant. So for example, some manufacturer has come up with some new refrigerant. Now what he wants to do, that manufacturer wants to check the forced convection characteristics of this particular type of refrigerant before uh, uh, using this refrigerant into the practical conditions. Okay, so what this refrigerant manufacturer has done, they have contacted some testing laboratory and they have supplied some input parameters of this refrigerant to that testing laboratory, and they are asking the testing laboratory actually to design some experimental facility for obtaining the forced convection characteristics of this particular uh, refrigerant. Okay, so what are the properties they have supplied? They have supplied that we are having refrigerant in the form of saturated liquid, and its temperature range in which it will be working, that is from 0 to 40 degrees Celsius. Okay, density of this saturated liquid refrigerant is under the given range of temperature is nearly equal to 1200 kg per meter cube. Its corresponding saturation pressure value is also specified, that is changing from 300 to 1000 kilopascals. Dynamic viscosity is also given, thermal conductivity, specific heat, Prandtl number, and then while we have to do actually the measurement of forced convection characteristics, obviously our fluid should be under bulk motion. Okay, so because of that, we will be having some flow Reynolds number of the refrigerant. So the desired range of flow Reynolds number is also given, that we have to determine the convection characteristics of this particular refrigerant within the range of 20,000 to 1,50,000 Reynolds number value. Okay, fluid is remaining in the liquid phase only. Okay, and flow geometry within which we have to do the testing, that is nothing but a smooth circular tube, and the diameter of the tube is actually ranging from 2 mm to 35 mm. Okay, so when we have to do the measurements, then we have to actually determine the forced convection characteristics within the range of 2 mm to 35 mm tube diameter. Okay, and tube length, so there is no information given about the tube length, just it is written that it should be sufficient for the flow to become fully developed. It means we have to determine the forced convection characteristics under the fully developed flow situation. Okay, then next is temperature difference between the tube and the fluid. So it means we are having nothing but a situation of internal flow where we will be having some heated tube, and we will be having the flow of refrigerant through this heated tube. So the range of temperature difference in between the fluid and the heated tube should be from 5 to 15 degrees Celsius, under which we have to actually do the measurement. For heat flux, it is given that as determined in the experimental design. So it means depending upon the experimental design, we have to consider the value of heat flux. Flow rate also we have to consider as per the requirement of the experimental design. And we have to also determine desired uncertainty in the determination of heat transfer coefficient. Okay, so we have to see that whatever the experimental setup we are designing, whatever the instruments we are using, depending upon their measurements, what is our uncertainty limit in the measurement of heat transfer coefficient. Okay, so this is like input. These are the input parameters which are specified by refrigerant manufacturer to the testing laboratory. Okay, now you consider yourself as nothing but an engineer for that particular testing laboratory, and you have to now design the experimental facility for obtaining the heat transfer coefficient of this new refrigerant. Okay, so let us now try to see what we have to do, how we have to approach to this problem. Okay, so now at this very first moment, you should be very clear about the type of the experimental setup, because we have to measure the convective heat transfer coefficient, and already I have told you in our earlier lectures that what is the general layout of the experimental facility for obtaining the heat transfer coefficient. Okay, so same schematic photograph I have included over here. So this schematic photograph is nothing but a tube, and through this tube we will be having the flow of refrigerant. Okay, we will be having flow of refrigerant through this tube. Then we will be having some thermocouples attached to this tube, which will be actually measuring the temperature of refrigerant at the inlet and temperature of refrigerant at the outlet. Okay, in order to measure the flow rate of the refrigerant, we will be employing a flow meter. Then whatever the tube we are considering, to this tube we will be supplying some current and voltage. Okay, so we will be having ammeter and voltmeter for obtaining the voltage and current whatever we are supplying to this particular tube. Okay, and then we will be having a series of thermocouple mounted on the surface of the tube in order to determine its wall temperature. And at the same point of time, what we want to do, we want to determine the value of heat flux. Okay, so for that purpose, I have already told you what we have to do. The tube surface we have to actually insulate perfectly, so that whatever the amount of heat we are adding, that entire heat is actually entering into the refrigerant only. Okay, so this schematic arrangement of the experimental setup already I have discussed. But now comes the point that whatever the thermocouples we are using for measurement of the temperature, what should be their range, what should be their type, and what should be the uncertainty in our measurement of temperature, which is actually giving us uh, conditions or our final uncertainty in the measurement of heat transfer coefficient within the acceptable limit. Okay. Same way, we are having large number of devices available for the measurement of flow rate. For example, we are having turbine based flow meter, vortex type flow meter, magnetic flow meter, Coriolis mass flow meter. So large number of flow meters are available. Okay. So for this particular system, based on our some preliminary analysis, we have to determine that what type of flow meter we should use. Similarly, for other devices also, that what range of ammeter and voltmeter is required. Okay. So for that, what we have to do before even designing the experimental setup, what we have to do, first we have to do some preliminary analysis based on our theoretical understanding, and then we have to first obtain what is the expected range of different parameters within which our actually system will be system has to be designed. Okay, so for that purpose, what I have done over here, first I have actually considered a situation that let us first try to estimate the value of heat transfer coefficient which we actually experimentally want to measure. Okay, but what we will be doing Now we will consider from our literature or from our theoretical knowledge that what are the different heat transfer coefficient relations available, and what is the generalized relation which can fit our data. So for that case, what I will be doing, because we are having the requirement of Reynolds number within the range from 20,000 to 1,50,000. So that's why I will be taking over here the correlation of heat transfer coefficient which is applicable for turbulent flow. Okay, so for turbulent flow we are having very famous equation already known from our literature. That particular equation is known as Ditus-Boelter equation. So as per Ditus-Boelter equation, Nusselt number is nothing but equal to 0.023 into Reynolds number power 0.8 into Prandtl number n. Okay, and in this particular equation, actually what we are having value of n equal to zero point 0.4 if we are having heating of the fluid medium, and this value is equal to zero point 0.3 if we are having cooling of the fluid medium. Okay, so the difference between heating and cooling is when our pipe surface is hot and fluid is gaining the heat from the pipe surface, then we say the situation of heating and we take the coefficient n as zero point 0.4, and if we are having our pipe surface as cold medium and fluid is actually transferring the heat to the pipe, then we take the value of this coefficient as 0.3. Okay, and this Nusselt number definition we already know it is nothing but equal to h d by k, where h is our heat transfer coefficient, d is internal diameter of the pipe, and k is our thermal conductivity of the fluid medium. Okay, so now what we are having extreme ranges of the pipe diameter as 2 mm and 35 mm. These are our two extremas. Okay, so and Reynolds number limit is from 20,000 to 1,50,000. Okay, so initially for Reynolds number of 20,000 and pipe diameter of 35 mm, if I try to find out the value of heat transfer coefficient, that is coming around 271 watt per meter square degree Celsius. Then if I consider the same value of Reynolds number and if I take the lowest pipe diameter, then value is coming around 4740 watt per meter square degree Celsius. Okay. Similarly, I have obtained the corresponding value of heat transfer coefficients for Reynolds number value of 1,50,000 and two different pipe diameters. Okay, so this is nothing but from this particular analysis we have got actually rough estimate of our heat transfer value, heat transfer coefficient. Okay, so means this is nothing but our expected output of heat transfer coefficient from our experiment. Okay, so this will be only applicable if our refrigerant, whatever this manufacturer has developed, that is actually following this correlation. Okay, if it is not following, then obviously our value of heat transfer coefficient may deviate, but because this equation of Ditus-Boelter, it's actually generalized equation irrespective of the type of fluid. So that's why our value of final heat transfer coefficient should be close enough to the values obtained over here. Okay, so if our values are changing significantly, then obviously we have to once again relook into our experimental measurements. Okay, so this is the initial estimate of heat transfer coefficient based on our theoretical knowledge. Then what we have to do now because manufacturer has only specified the range of Reynolds number. Okay, now depending upon the value of this Reynolds number, what we have to do actually, we have to determine the amount of flow rate. Okay, so what amount of flow rate we have to supply in order to meet this Reynolds number condition. So we know the definition of Reynolds number is nothing but equal to rho into average velocity into the pipe multiplied by internal diameter of the pipe divided by dynamic viscosity. Okay, so what we have to do over here for different limiting pipe diameters and the limiting Reynolds number conditions, we have to determine the corresponding value of mass flow rate. Okay, so for Reynolds number of 20,000 and diameter of 2 mm, if we calculate the corresponding value of mass flow rate, we are finding it as nothing but 9.42 into 10 to power 2 kg per second. Then for 35 mm pipe diameter, it is coming as 2.89 kg per second, and then corresponding to Reynolds number of 1,50,000, our range of mass flow rate is actually 0.0712. Final value is 21.6 kg per second. Okay. So from this you can see that we are getting actually the lowest mass flow rate as 0.071 kg per second, and highest mass flow rate we are getting as 9.42 into 10 to power 2 kg per second. Okay. So from this measurement of the flow rate, we can see that we are having actually very wide range of flow rate. So we will not be having individual flow meter, a single flow meter we will not be getting, which will be fulfilling our entire range of flow rate requirement. Okay, so it means that if we have to do the experiments for the entire range of pipe diameter, particularly varying from 2 mm to 35 mm, we have to actually use the multiple or different instruments for measurement of a single physical parameter. Okay, because we are getting a wide range of flow, so it means we require different types of different flow meters, particularly in order to perform our experiments. Okay, so what we will be doing at this particular moment, because always it is not recommended to replicate a number of similar type of devices. Rather, what we do, we try to take uh, more specific, or I should say more mm, a physical situation which is actually representative of the entire range of parameters. Okay, so based on that we first try to obtain some output, and if that output is following a specific trend and it is correlating to some known relation, known theory, then we need not to repeat the experiment for each and every situation. Rather, based on that single experimental data only, we can determine the final correlation. Okay, so that is what we will now be trying for this particular experiment. Now we will take an assumption that instead of using or designing the experimental setup separately for a 2 mm tube diameter, then for a 35 mm tube diameter, and similarly then for intermediate range we may have to take some one more tube diameter, say corresponding to 25 mm, 15 mm, 10 mm. So if we are designing multiple number of experimental setup, rather than that, what we will be doing now at this present moment, we will go with a single tube diameter, and we'll consider that it is nothing but a representative of the entire range of Reynolds numbers as well as the entire range of tube diameters. Okay, so considering that particular situation, I am now freezing tube diameter to 12 mm. Okay. One more thing, 12 mm, why I have taken it is actually commercially easily available. Okay. So when we are purchasing the tubes in the market, either we are having tubes of 1 inch, half inch. So as per the standard availability of the tube also, we are having actually availability of 12 mm diameter tubes. Okay. So based on that, I have actually now freezed over here the diameter of the pipe. So what we will be doing first, for using this particular diameter, single diameter, actually we will be doing our experiments. And if our experiments are actually correlating, giving a good correlation, then obviously we need not to replicate number of experimental setups in order to meet the entire range. Rather, based on the correlation whatever we have got, actually we can estimate the value of heat transfer coefficient within some certain acceptable range of uncertainty. Okay, so here I have freezed the tube diameter as 12 mm. Now let us first try to see the value of heat transfer coefficient also. So sorry, heat transfer rates also. So for heat transfer rates, if we are having pipe of 2 mm and another situation is we are having pipe of 35 mm, then obviously what we will be doing now, we have to select some length also in order to ensure the fully developed flow condition. Okay, so our L by D ratio should be large in order to ensure fully developed flow condition. So at present what we are doing, considering the constraints from practical scenario, as well as uh, taking the theoretical understanding that we should have sufficiently large pipe in order to have fully developed flow situation, I am actually taking the length of the pipe as nothing but equal to 2 meter. Okay, so if I take length of the pipe as 2 meters, so what will be happening? My surface area over here is coming to be 0.0126 meter square for smallest diameter pipe, and for largest diameter pipe it is coming to be 0.22 meter square. Okay, so you can see now for different values of Reynolds number, because H, limiting H, we have already determined. So, and we are having the limiting conditions of uh, temperature in between wall and the fluid ranging from 5 to 15 degrees Celsius. So let us first try to determine the heat transfer rate corresponding to 15 degrees Celsius. Okay, so corresponding to 15 degrees Celsius, you can see we are getting 896 watt, 894 watt as the minimum value for requirement of the heat transfer rate, and maximum value of requirement of heat transfer rate is nothing but 488. Okay, so it means that if we have to use our electrical circuit or electrical voltage and current input to our for our resistance fitting, then this is the actually range of heat transfer rate which is required. Okay, because if we consider that we are having perfect insulated situation, in that case what will be happening? Q will be equal to nothing but equal to V into I, that will be equal to mCp into T2 minus T1, and that will be once again equal to H times uh, area into T wall minus T fluid. Okay, so all these different conditions actually should satisfy if we are having the perfect insulation and we are having the complete energy balance. Okay, then if we now try to see that how much our temperature of the fluid will be changing, so corresponding to the Reynolds number of 20,000 and diameter of 2 mm and length of 2 meters, if we are considering 896 watt as our requirement of the heat, and that requirement of the heat once again then we will be changing depending upon the type of pipe diameter. Okay, so we know that Q is nothing but equal to mCp into T2 minus T1. So mCp into T2 minus T1 I can simply write as delta T of fluid. Okay. So from this relation we are finding that change of temperature for the lowest tube is actually 67.9 degrees Celsius, corresponding to lowest Reynolds number. And then for largest pipe diameter it is actually 0.22 degrees Celsius. Then it is 45.2 degrees Celsius in another case, and it is 0.148 degrees Celsius. Okay, so you can see once again the change of temperature is also actually varying over a wide spectrum. For few situations we are having actually change of temperature as very small value, and for few cases we are having actually large changes in the temperature. Okay, so it means once again, while we will be actually, if we are using device for measurement of the temperature, and if we are using the different tube diameter, say 2 mm and 35 mm, then obviously for some situations we have to employ, particularly for 35 mm diameter pipe, we have to employ actually very precise thermocouples for measurement of the temperature. Here we are having range of measurement as very small, whereas high sensitivity is required. Okay, if we take another situation of diameter of 2 mm, there actually the requirement of the range is very large, whereas our measurement of temperature is not that much sensitive. Okay, so all these are the constraints that if we are using the entire range of tube diameters, then obviously depending upon the different tube diameters, actually we have to change the instrumentation also in order to perform our experiments. Okay, so considering all these limitations at this stage, what we will be doing first, we will be now freezing our tube diameter. So I have already told you that I am considering 12 mm as nothing but a representative tube diameter for the entire range. Okay, so that's what I have done over here. Now what I will be doing, whatever the calculations we have done earlier, these calculations now will be nothing but repeating for diameter of 12 mm and length we have considered already as 2 meters. Okay, so and few more constraints I am taking. I am considering that at the inlet our temperature of refrigerant is nothing but 0 degrees Celsius. Okay, And when we are calculating the heat transfer coefficient, so our maximum change of temperature in between the wall and the fluid is actually 15 degrees Celsius. So if we consider all these constraints corresponding to that, for the given range of Reynolds number of 20,000 and 1,50,000, these are the corresponding values of mass flow rate, heat transfer coefficient, rate of heat transfer, and uh, change of temperature. Okay, so particularly you have seen that earlier our range of mass flow rate and the change in temperature was actually varying significantly. Now, if we fix the tube diameter to 12 mm, then the change in mass flow rate range is actually of one order only. Okay, so here you can see the lower value is 0.0566 and highest value of mass flow rate is 0.424. It means a single flow meter, something like vortex type flow meter or turbine type mass flow meter will be actually serving the purpose. Similarly, for measurement of temperature, we are having actually range varying from 11.13 degrees Celsius to 7.55 degrees Celsius. So that also we will be able to measure with the help of single type of thermocouple. Okay. So now what we will be doing, we have now freezed our geometric details of the experimental setup. Now we will be, and we have also got the range of parameters within which we need to do the measurement. So now we will be actually finding our measurement instruments. Okay. So these are some of the proposed measurement instruments and methods. So for example, if I have to measure individual value of T1 and T2, then I can take type E thermocouple whose range is actually from 0 to 40 degrees Celsius and estimated uncertainty is plus minus 0.5 degrees Celsius. Okay. Then we are having, apart from using the individual thermocouples for measurement of temperature T1 and T2 at two different locations, we can use a thermopile arrangement also. So in case of thermopile, what we will be getting actually, we will be getting more accurate estimation of change of temperature only. Okay. So if we use the thermopile arrangement, once again, we are using E-type thermocouple only in order to fabricate our thermopile sensor. So for that, we are having T2 minus T1. Directly, we will be getting the temperature difference, and that temperature difference is range is actually 0 to 15 degrees Celsius, and uncertainty is plus minus 0.3 degrees Celsius. So it means if we are using the direct measurement of difference in temperature at inlet and outlet using the thermopile, then we will be having lesser uncertainty in our measurement of temperature. Okay. For wall temperature, obviously that's a single quantity, so we cannot use thermopile. Once again, what we will be using there, we will be employing the thermocouples, and range of measurement we are considering 0 to 60 degree. Why? Because if we are highest temperature of the this fluid is actually 15 degrees Celsius, and at the same point of time we are having actually 15 degrees Celsius as the difference between the wall temperature and the fluid temperature, then obviously we will be having significant range of wall temperature for obtaining its value. Okay, so that's why we are considering slightly more in comparison to the fluid. So we are having the range of measurement in the value up to 60 degrees Celsius, and uncertainty will be plus minus 0.5 degrees Celsius. Okay, for flow rate measurement, we have considered turbine type flow measurement device. It's having a range of measurement from 0.05 to 0.5 kg per second, so that actually fits our required range of flow rate. Okay, and uncertainty we are having plus minus 0.5%. Corresponding voltmeter and emitter also we have selected. Okay, and for pressure measurement, though we are not having any requirement for the measurement of pressure, but still if we want to measure the pressure within the tube, then we can simply use Bourdon type gauge, and if required we want to store the signal of the pressure, then we can employ transducer also. Okay. Now let us try to see that what will be the uncertainty associated in measurement of heat transfer. Okay. So the value of heat transfer we can determine by two methods. So one is like we are knowing the temperature difference T2 and T1. Okay. So that we are calling as nothing but delta T fluid. So that we are measuring with the help of a thermopile arrangement, and at the same point of time we are measuring the mass flow rate m dot with the help of turbine flow meter, and Cp we are already knowing from the manufacturer of the refrigerant. So I can determine Q as nothing but equal to m dot Cp into delta T fluid. So that is the one method of obtaining the heat transfer, and another method of obtaining the heat transfer can be Q is nothing but equal to V into Y, because we are already measuring the voltage and current which we are supplying to our system. Okay. So what we will do at this particular stage, we will perform uncertainty analysis. Okay, and with the help of uncertainty analysis, we will try to see that which mode or which method actually gives us less uncertainty, and that particular method then we will employ for measurement of the heat transfer. Okay, so for Reynolds number 20,000, you can see when we do the when we apply this Klein and McClintock equation, we are finding uncertainty in heat transfer as 2.7%. If we are using the flow energy method, Q equal to mCp into delta T fluid. And if we are using electrical power based measurement method, then we are getting the uncertainty as 0.42%. Okay, sorry, 0.042%. Now you can see that while we have applied the Klein and McClintock equation, so we are having the requirement of individual uncertainty values. So individual uncertainty value, what we have done, we have taken from the table which is given in the previous slide. Okay, because once we have finalized the instruments, then obviously we are knowing their individual uncertainty value, then we will be finding that how these uncertainties are being translated into our final output quantity. Okay. Then corresponding to Reynolds number of 1,50,000, we are having once again, if we are employing the flow energy based method, then we are having percentage uncertainty as 4.1%. However, using the voltage and current, once again, the uncertainty value is actually very, very small, which is 0.042%. Okay. So from here, one of the estimate comes that if we are using the voltage and current, then obviously we will be able to determine more accurately, or within we'll be having precise control on measurement of our heat transfer, whatever we are subjecting our tube to. But we cannot always ensure the perfect insulation in between our medium and the surrounding. Okay, in our heating medium and the surrounding. So there are chances always that we will be having certain heat loss into the surrounding. So because of that, what we have to do, we have to actually consider this particular flow energy based uncertainty only into our measurement of the final output. Okay, why we are considering? Because if we are having perfect insulation, then obviously this electrical power output based method will be giving us the very precise measurement. Okay, but in our actual practice, we cannot ensure that whatever the energy we are receiving from the electrical power input, that same energy is actually being transferred to the fluid. Okay, so that's why what we have to do, while we will be deriving the value of heat transfer coefficient, we will be using the flow energy method for estimation of heat transfer rate. Okay, so in flow energy method, we are getting the value of uncertainty as 4.1%. Okay, that also when we are considering the ideal situation. Now, but in our actual practice, what we will be having, we will be having some leakage of heat into the surrounding. So because of that, what we are considering at this moment, we will consider that we are having uncertainty in measurement of heat transfer as 10%. Okay, so why I am considering this 10%? Our actual ideal analysis is giving the value of 4.1%, but we are not actually accounting for the losses which are happening to the which are inherently with our experimental facility. Okay, so because of that, we are actually taking slightly more range of uncertainty in measurement of heat transfer. Okay, so what I have done, I have specifically limited our uncertainty in heat flux measurement to 10% over here. Then now let us try to do the calculation of heating device. So we are having internal diameter of the tube as 12 mm, and from our commercially available pipes, we are having the thickness of this corresponding to this particular diameter as 0.8 mm, length we have considered 2 meter, and if we are considering the stainless steel as material of the tube, then from the properties of the stainless steel, we know the resistivity of pipe as nothing but 70 micro-ohm per micro-ohm centimeter. Okay, so for this given geometric parameters, by using the by using the relationship in between the resistance and resistivity, we can determine the resistance of the pipe material. So our resistance of the pipe material is coming out to be 0.0435 ohm. Okay, so if this is our resistance, we have already seen that our limiting flux limits are nothing but 894 and 4480. So corresponding to the limiting flux limits, what I have to do, I can determine that power as nothing but equal to either E square by R, or I can also use I square into R. Okay, so using these two relations, now already we are having the known value of resistance of the tube surface, so we can determine the value of current and required value of voltage. Okay, so corresponding to minimum and maximum power, the current is actually changing from 143 to 321 ampere, and our voltage requirement is from 6.22 to 14 volt. Okay, so while we are selecting actually our battery or input power device, so this range of current and voltage this particular device should satisfy. Okay, then what we will be doing now, if we are now what we will be doing, because now we have identified all our devices, what will be the requirement of power input. So now we will be fabricating our experimental setup, and we will be taking the measurements. Okay, so once we have taken the measurement, after that what we have to do, we have to determine or obtain the value of heat transfer coefficient. So heat transfer coefficient is nothing but equal to Q divided by surface area into TW minus TF. So TW minus TF we are considering as delta T. So now let us first identify the uncertainty in measurement of delta T. So in measurement of delta T, uncertainty will be 0.5 square plus 0.5 square, and one typo is over here. It should be actually square root of that. So finally, we will be finding that 0.71 degrees Celsius is nothing but our uncertainty in the measurement of delta T. So how this 0.5 is coming, that I think you are already now knowing. Our delta T is equal to TW minus TF. Now, if we apply this equation of Klein and McClintock, then we will be having over here del TW divided by TF. Okay, so that will be giving us the corresponding measurement of uncertainty in individual these two temperatures. So that's why we are getting final temperature uncertainty as 0.71 degrees Celsius. Okay. And already for heat flux, apart from that, A is coming from the geometric detail, so that we are considering as constant parameter, which is already known. So another measurement we are doing for the heat flux, and for heat flux, I have already told you that I have considered the value of uncertainty as nothing but 10%. Okay, so why we have considered 10%? Because some of the heat leakages will be taking place into the surroundings. Okay, so now if you apply this particular Klein and McClintock equation for heat transfer coefficient formula, finally we will be finding uncertainty in the measurement of heat transfer. So corresponding to 5 degree Celsius change of temperature, we are having uncertainty of 14.2%, and with reference to change of temperature of 15 degrees Celsius, we are having uncertainty in heat transfer coefficient as 4.83%. Okay, so what we will be doing now, we have to select nothing but the situation corresponding to least uncertainty, so that we can give the precise correlation of heat transfer coefficient. So that's why what we will be doing, we will try to do our experiments under the situation where we are having actually 15 degrees Celsius as the difference of temperature in between our wall and the fluid. Okay. So if you do the experiment, if you perform the experiments, you will be finally finding the corresponding value of Nusselt number, as well as the Reynolds number is our input parameter, which basically we will be obtaining with the help of flow meter, because with the help of flow meter we will be determining the different mass flow meters which our experimental setup is subjected to. Okay, so if we plot Reynolds number versus Nusselt number into Prandtl number to the power 0.4 plot, so nothing but by considering that it is following the existing correlation of Ditus-Boelter equation. So our experimental data should follow this particular trend over here. So this is nothing but I am saying as expected results. So once you do the experiments, then you will be finding that what type of results you are getting. But if it is following the Ditus-Boelter equation, then this is some expected result, expected trend that your results of heat transfer coefficient should follow. Okay, but before directly jumping into the value of heat transfer coefficient, it becomes important to first obtain the value of temperature and plot that value of temperature as function of distance. Okay, so obviously what will be happening, we are doing actually uniform heating of the pipe. Okay, so as we are doing uniform heating of the pipe, because of that what we will be having, the surface this fluid will be actually subjected to condition of constant heat flux. Okay, so already for a fully developed flow situation we know that temperature versus x plot for fully developed flow nothing but shows a linear increase in wall temperature as well as the linear increase in fluid temperature. Okay, so fluid temperature we are measuring at inlet and outlet, so obviously we will be taking the linear approximation. So because of that, if I have to define bulk mean temperature T bar F, because the variation of the temperature is linear along the length, so bulk mean temperature I can determine as arithmetic temperature. Okay, so I can write T bar F as nothing but equal to T1 plus T2 by 2. Okay, and for wall temperature what we are having, at we are having number of thermocouples. So obviously from the thermocouples we will be getting the individual value of temperature. Now in our final equation for obtaining the heat transfer coefficient, Q will be HA times T bar W minus TF bar, where TF bar is bulk mean temperature of the fluid, which is equal to T1 plus T2 by 2, and T bar W will be nothing but whatever the value of temperature we are getting, TW1, TW2 plus so on up to TWN divided by N. So once again it will be the arithmetic mean of the number of thermocouples which are mounted along the length of the wall. Okay, so this is also like immediately after doing your experiment you can plot the wall temperature and fluid temperature, and you should have your measurement of wall temperature and fluid temperature close to that of the linear profile. Okay, because then only our condition of constant heat flux will be satisfied. Okay, and once you are obtaining these relations as expected, in that case whatever the heat transfer coefficient you are getting, that will be also accurate. Okay, so this is how like we go for the design of experimental setup. We first do some preliminary analysis based on our theoretical understanding, and based on that preliminary analysis actually we find our range of parameters, and once range of parameters is actually freezed, then we uh, take different measurement instruments, and once measurement instruments are finalized, then obviously while finalizing the measurement instrument we do actually uncertainty analysis, because uncertainty analysis will be giving us idea that what type of instrument we should select. Okay, and how much uncertainty we will be getting in our final output. So uncertainty analysis has to be done prior to the selection of the experiment, prior to the selection of the instrument. Okay, because first we will be say taking one type of instrument. If it is giving very high uncertainty in our final measurement, then obviously we will be selecting some precise instrument of low uncertainty. Okay, so uncertainty analysis has to be done prior. Then obviously whatever the raw data we will be getting, for example temperature profiles, that also we should, though that will not be going into the final report, but that we should plot for our own understanding and confidence whether our experiments are actually um, following the theoretical trends or not. Okay, because if with the help of this raw data we are able to get the theoretical trends, then obviously we will be having more confidence on our final output. Okay, now in this particular situation you have seen though we have not done experiment, but we have shown that okay, our results will be actually expected to follow the Dietz-Bolte equation. So if our results are following the expected results, then obviously we need not to repeat the experiments for 2 mm and 35 mm tube diameter. We can consider that our refrigerant is actually following the same trend. Okay, but if we are having significant variations in our result and the expected results, then obviously we have to change the tube diameter as well as the necessary instrumentation, and then we have to repeat the experiments in order to get more confidence on our coefficient, and that new coefficient then has to be new correlation has to be then developed. Okay, so this is like whole idea of design of experiment to a physical situation. Now what I have done here, I have actually given uh, an summary of the different procedures what we have followed in solving this particular problem, and then what type of final data sheet and calculated results we will be actually obtaining. So this flow of the different activities which we have performed, that is actually specified over here, and this particular data sheet has to be now obtained before the experiments are being started. Okay, so you can see first we are doing the general observations. For example, we are recording ambient temperature, type of material, then calibration of the different instruments. Then we are doing primary measurements, well, measurement of T1, T2, TW, voltage, current, delta T. Then geometric details we are determining. Then we are estimating the uncertainties in our primary measurement. Then we are calculating our different parameters which are required to obtain the final output H, nothing but heat transfer coefficient. Okay, so then what we are doing actually is we have to check that whether our experiments are correct or not. What we can do, we can apply this particular check that E into I should be equal to MCP into T2 minus T1. Obviously, that will not be exactly matching, but it should be close enough to each other. Okay, so if we are having significant difference in between these two, then obviously we can ascertain that our experimental setup is actually not correct. Okay, and we have to improve it. So this is nothing but a final data sheet. As per this particular data sheet, actually we have to perform our experiments and then obtain the final value of heat transfer coefficient. Okay, so now what I will do with this discussion, I will stop at this point, and I believe that this particular example has helped you in understanding the whole process of designing an experimental setup for experiments related to fluid and thermal engineering. Okay.